Exercise 44. We want to show that a linear transformation from R3 to R3 preserves length if and only if the matrix of this linear transformation satisfy the condition transpose multiplication with itself is identity. So this is actually we know that if you got an orthogonal columns of a matrix, which mean that if you have U and by a matrix with orthonormal basis, with also normal columns, which means orthonormal basis for the column space of U, then actually we know that the matrix transformation, so this U is a matrix transformation from Rn to Rm, mapping column vector to column vector, different size of course. Then it preserves the length. So we're talking about the dot product of Rn, for example, and then you have a notion of length, angle, whatever. And of course, it's not really limited to dot product of whatever inner product. And correspondingly, you have orthogonality length. Secondly, preserves orthogonality. So dot product. So here we are talking about dot product, just to make the statement simple. Let me just put it more simply. Like the same dot product. In particular, the orthogonal, the image orthogonal if and only if this is orthogonal, right? You could think of this as a sub-exercise. This is a remark and also sub-exercise. So for example, let's first look at this sub-exercise. Just recall what is matrix multiplication of a matrix with a column vector. That is, by definition, just we suppose coordinates x1, x2, xn. And this is just x1, u1, x2, u2. Scalar multiplication, xn, un. And so dot product with itself equals dot product with itself, because this is also normal basis, and so what is left is only finally, obviously, xi squared. And in particular, this is the product. And in particular, this implies the square root on both sides are the same. They have the same norm, right? And secondly, let's look at this dot product. So again, with similar notation, I mean y with component y1, y2, yn. Let me just do the computation. We'll have summation xi ui dot product summation yj uj, and again by orthonormal basis ui we have x1 xi yi summation I from 1 to n, and this is exactly the dot product of x with y. Okay, let's say call this the first part. The second part, let's say that ut matrix multiplication with u equals identity of n if you had also normal column. Because just by computation, this matrix multiplication is un transpose, and then multiplication with u1, u2, un. So first row, first column, give you u1t, u1. Similarly, for each entry, you got ui transpose matrix multiplication uj. This is also ui dot product with uj as vector, and so on. Also normal. This is identity matrix, right? So this is the basic situation. What do we know? And this exercise is kind of telling us kind of generalization of this and give you the full results. So the first thing would be actually, so to fit our remark or sub-exercise into this is we observe that this description is equivalent to say MS has also normal column. Right, because so let me put this as third exercise, third sub-exercise, because firstly, if you have orthonormal columns, then you satisfy this. This is what we have proved here, right? This is okay. This is our 2. So this direction, suppose you have your ut times u equals in, but this implies we have also normal columns. The answer is yes, because again, by the same description, this is just your i's column dot product with your j's column, and then denoted as your ij's column. So if this equals in, this equals in is equivalent to tell you ui dot uj equals 0 if I different from j, right? And 1 if I equals j, 0 else where, and so this is also normal. So basically what we're familiar with is already telling us or also normal column implies or is equivalent to this matrix characterization. What we want to show is that this is further equivalent to the linear transformation preserved length. So this direction is okay. We have already showed that preserves length. So solution of exercise 44. So this is okay. This is proved. Also normal column preserved length. So what we have to show is this. If a matrix transformation preserves the length, then would it be a matrix which has orthonormal columns, or differently putting, matrix satisfying that condition? So let's do in several steps. So let's say if our linear transformation S preserves length, then in particular it preserves dot product. Actually this is equivalent to it preserves dot product, because just take square root. And so this is equivalent to say for any u and v are free, so su dot product with sv equals u dot product with v, right? This is our observation. And then this is saying ms u dot product with ms v equals u dot product with v. This is equivalent to say, put it differently, instead of using dot product, let's use matrix multiplication. So u transpose m, let me just write m instead of writing ms. M v equals u transpose v, right? Now here comes sub exercise, equivalent to mt m equals identity 3. So this exercise is actually saying that, let me put it more generally, let A be a matrix 3 by 3 row entry, show that if you have whatever vectors v and w satisfies vta, w equals vtw, or whatever v and w are 3, then this A must be identity. This is the sub exercise, and in particular here, that's applying this sub exercise, we will have mt times m equals identity. That's what we want to prove. Okay, so we are only left to prove this sub exercise. So obviously we just use some special testing element to show that, testing vectors v and w to show that all the entries of A corresponds to identity matrix. So let's take testing vectors. In particular, let's take v equals EI, the standard basis, with only i's component 1 or the other 0. And WEJ, then what is the EIT? EJ, this would be let me put it transparently. So this is the i's, this is the j's. So what you got is this is 1 by n, and by 1 this would be 1 by 1, right? So this would be either 0 or 1. If I different from j, this will be 0. If I equals j, this will be 1. This is the right hand side, right? And on the left hand side, what do you got by this? Let's again put it transparent. Let's put this A here, right? And so this would be just first row, first column, thinking of A as column vectors. And so this would be first row, first column. So 1 by n times by three by 3 actually. Okay, so I'm actually proving something much more general. So let's say A is Mn of R. So this would be each AI is n by 1 column matrix. So this all together is n by n. So this is 1 by n, n by n. Finally, I'll give you 1 by n. So first row of this part gives you first row, first column. So it cut out the i's entry of your first column, right? Let's call it AI1. Because it corresponds to ith row, first column of your matrix A. Similarly, you got your AI2, AIN, and then multiply with this J's row 1. Like this, think of this as 1 by n by 1. So again, this cut out this AIJ. So on the left hand side, you got AIJ. On the right hand side, you got this delta IJ, right? And this is telling you that AIJ equals 1, I equals J, 0, I different from J. This is telling you that A is identity. Actually, we proved a more general exercise. You see, it's not only for M3, we proved for Mn, and for any n vectors in Rn, we have proved this is an identity matrix. Okay, finish the proof.